Welcome to this tutorial. In this video, I'll be demonstrating how to formulate a linear programming problem for a transportation problem. Alright? Without taking much of time, let me get to the example. So we're saying formulating a linear programming problem, LP, for the transportation problem. Now, when we discuss transportation problem, we are looking at a problem, for instance, where we have warehouses. Okay, we have warehouses which are supposed to supply. Maybe there are two. Let me just say there are two, which are supposed to supply maybe to 3 retail shops. Okay. 3 retail shops. So what would happen is there's a possibility that warehouse 1 can supply to retail shop 1, and it can also supply to retail shop 2 and retail shop 3. And all these who have their cost, their shipping cost from moving from warehouse 1 to retail shop 1, retail shop 2, and retail shop 3. Likewise, warehouse 2 can also supply to retail shop 1, retail shop 2, and retail shop 3. So we are basically looking at such a scenario where we have this kind of an arrangement where you have warehouses which are supposed to, or maybe a manufacturing factory which is supposed to take goods to warehouses and something like that. So we're just formulating a problem which can be solved using the 3 common transportation models, which is a northwest corner, least cost method or lowest cost method, and the Virgil approximation model, which is basically VAM. Okay. Now, my area of concentration today is not basically to solve using VAM, but in my next videos, I've demonstrated the same problem, how it is going to be solved using northwest corner and least cost method and VAM, which is Virgil approximation model. So the first question is formulate a balanced transportation problem. So we have a problem here. Let's read through. Company X has 3 warehouses located in Lusaka. The daily supply capacity is as follows. Warehouse 1 has got a capacity to supply 7,000 kgs. Warehouse 2 has the capacity to supply 4,000 kgs, and warehouse 3 has the capacity to supply 10,000 kgs. Each day, the company must meet the demands or the needs of each 4 retail shops. The minimum requirement of each retail shop is as follows. Retail 1 requires 7,000 kgs, all right. Retail 2 requires 5,000 kgs, retail 3 requires 3,000 kgs, and retail 4 requires 2,000 kgs. Cost of shipping in dollars for each kg is given below. So we have got a table here which demonstrates the cost, which has given us the cost of shipping. You can see this is retail 1. So for example, if warehouse 2 is to ship to retail 3, the cost is $6, as the case would be. All right. So as you can see here, these are our retail shops. So the retail shops are the ones which are demanding. So this is possibly supply. These are warehouses. The warehouses are supplying. So the supply is in the rows, and the demand is basically in the columns, like this. This is demand. So always when we are dealing with transportation problem, we assume supply will be the rows and the demand will be the columns, like that. All right. Now the examiner has asked us to formulate a balanced transportation problem. Now let's see if this problem is balanced. If the problem is balanced, we simply say supply should equal to demand. That's how it should be. Alright, so let's look at supply. There is 7,000 plus 4,000 plus 10,000. We have 21,000. We have 21,000 in terms of supply. Okay, we have 21,000 in terms of supply. Let's look at demand. Yes, 7 plus 4 plus 10, that gives us 21. Yes. Okay, let's look at the demand. The demand, we have got 7,000, 5,000, 3,000 and 2,000. The demand is only 17,000. All right. So the problem is not balanced. Demand is missing. So we can say 21 minus 17. Demand is missing 4,000. Okay. So we need to add 4,000 to demand. Now, as you can see, demand are these ones here. All right. So if demands are columns, it simply means that I need to add a dummy column with the demand of 4,000, which is going to have 0 cost, because that demand is not going to be fulfilled whatsoever. All right. That demand is not going to be fulfilled. Literally, it's not just there, but we just want to make the problem to balance up. So I'm going to add an extra demand so that the problem is balanced. Okay. There we go. So now let me do the balanced transportation problem. Solution 1. Okay. Solution 1. There I go. I said the one which is missing is retail. We've seen the demand is missing. The demand is only 17 when the supply is 21. So the demand, we need to add a dummy demand with 4,000 kgs. All right. Okay, so I have retail. So I have retail 1, retail 2, retail 3, retail 4. Remember, the retails are the ones which are missing. So I'm adding a dummy here. Dummy. Okay. I'll name it dummy 5. All right. So we have a problem which will look like this. Okay. And then here we have warehouses. Okay. We should have warehouse 1, warehouse 2, warehouse 3. Like that, yes. Let me explain this. I'll need it. And then we have something which is looking like that. This side we shall call supply. Why are we calling it supply? I did make mention that supply are our rows. These ones are supply. So the supply will be that, the supply will be that. Okay. And then these ones we shall call them as demand. So this is demand. Can you get it so that it's clear? This is our demand. Okay. So now our demand, we've been told our demand there is 7,000 for retail 1. So I'm writing 7,000 here. For retail 2, it's 5,000. For retail 3, it's 3,000. What a coincidence. For retail 2, it's 2,000. And then we have a dummy because the demand was shortfall and we are doing a balance problem. We have a dummy of 4,000. I named it dummy 5. It's just a naming. You can name it dummy 1, dummy 5. But it's just a dummy anyway. So I have a 4,000 here. Alright? Such that when I add 7,000 plus 5,000 plus 3,000 plus 2,000 plus 4,000, it gives me 21. Okay? Because the supply is actually 21. So supply 1, warehouse 1, which is warehouse 1 here, I'll put 7,000 there. Okay? Warehouse 2, I'll put 4,000 there. Warehouse 3, I'll put 10,000 there. And this gives me also 21,000. So when I add this side, it's 21,000. When I add this side, it's 21,000. So I have formulated what we are calling as a balanced problem. I'm just adding the cost. The cost in the dummy will be 0. Okay? Like I said, that demand shall not be fulfilled. And then I have 1 there, 5 here. I'm getting the cost from here as given by the examiner in the table. So I've responded to question 1 from the examiner. Now I need to respond to question 2. Okay? Question 2 suggests that we formulate the linear programming problem. Alright? We formulate the linear programming problem. So let's formulate the linear programming problem. Let's see what is going to happen. Having done that, I can remove this here and start working from here so that the computations are clear, the formulation is clear. Okay? So now let me remove this. Alright. So now I have that. Now I need to formulate the linear programming problem. So I've got retail 1, retail 2, retail 3, retail 4, and dummy. And then we say supply. Okay? And then I've got warehouse 1, warehouse 2, warehouse 3. Okay, I have a problem which is looking like this now, and then I'll have demand here, and then I've got that, and then this goes like this, this goes like this, and then I need to actually name them now. I'm going to define what we are calling as variables. I can call this as variable x11, this one x12, this one x13, x14, and x15, like that. And then 7,000 we know there, 4,000 we know there, 10,000 we know there, and here 21,000 as usual. And then I have x21, x22, x23. These are my variables. x24, x25. And I'm sure you can guess from here now, the way my mind is moving, this is x31, x32, x33, x34, x35. Okay? And then we have 7,000, 5,000, 3,000, 2,000, 4,000. All right. So now, having defined the variables like that, we know that the transportation problem is a minimization problem. All we are trying to do in this transportation problem is to minimize the total cost of shipping these goods, which are in cages, from the warehouse to the respective retail shops. Okay, so we're just trying to minimize the cost. So the objective function for this one is basically to minimize. Okay, so objective, I'll say minimize. Let me start properly. I'll need quite a good space. Objective, minimize. Okay, minimize z with respect to, now if you see, I'm going to write everything. This is going to be, okay, I'll protrude to this side. There's no problem. It's going to be a longer one. So we have got this one, minimize. The cost is 2x1 plus, okay, the cost is 3x12 plus, okay, the cost for this one is 11x13 plus, the cost for this one is 7x14 plus the dummy. We can put it there, but however, when we multiply 0 with anything, it will actually give us a 0. So for the sake of just showing, we can indicate a dummy, which is x 0x15. Okay, this is just for the sake of indicating. Otherwise, in the real result, this can be eliminated. But since we are formulating, let's just indicate it, and then we have again. I have to continue. We have the cost for these ones. This is 1, so this is 1x21, which is as good as x21 plus 1 again, which is x22. We cannot say 1x22. And then there we have got 6, which is the cost there. Okay, so we've got 6x23, and then there we have 1. It will be x24, and then there we have 0 plus 0x25. I must continue. Okay, no wonder I say it's going to be a longer one. So I'm showing the objective function, which is minimization, and then I say plus. Okay, if you have got enough space, it's just good to write it in one single row. Okay, so I'm done up to here. Then I come here. This is 5x31 plus 8x32 plus for 3, that's 15x33 plus 19x34 plus, okay, plus 0x35. I'm done. I've done everything. 1, 2, 3, 4. We're up to 1, 2, 3, 4, 5. Yes, 1, 2, 3. So there are 15 actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Correct. So we're done with that. Now we need to come up with the constraints, and then the constraints we simply say subject to. Okay? Subject to. Now subject to, we're basically looking at these ones now. Okay? So we have x11 plus x12 plus 13 plus x 15. This is as with regard to the supply, like that. This is as with regard to the supply. Okay, so now sorry, I missed 14 here. X15. Okay, this is with regard to the supply. Remember, the supply is more than the demand. So if the supply is more than the demand, it simply means that at the end of the day, we are going to remain with some units after we have fulfilled the demand for each retail shop. All right. So if we are going to remain with surplus, it simply means that we can allocate exactly or less than, because we've got more supply. So our symbol here is not going to be equal to, but it shall be less than or equal to 7,000. Why? Because we've got enough supply which is going to remain. So we're not going to actually supply everything. Alright, so I come back here. This is x21 plus x, I'm in that line now. x22 plus x23 plus x24 plus x25, and then less than or equal to 4,000. Again, I come to another constraint, which is x31 here plus x32 plus x33 plus x34 plus x35 less than or equal to 10,000. All right. Now I come again on the other constraints, which are these ones. All right, the retails. So now I'm going like this. This is x11 plus x21 plus x23. No, x31. All right, I'm going like that. Okay, should be equal to 7,000. Why am I saying equal to and not saying less than or equal to? Because I know this will be fulfilled completely. All right, it just has to equal to that, because that demand has to be fulfilled, because we've got enough supply and the demand is less, so all the demand will be fulfilled. So it shall just be equal to. All right, and then I come to this one, x12 plus x22 plus x332. Yes, x32 equal to 5,000. Okay, and then we come here. We have x13 plus x23 plus x33 equal to 3,000. Okay, and then we come here, x14 plus x24 plus x34 equal to 2,000. For the dummy, we can put it there for the sake of fulfilling the transportation model, but this demand is not going to be fulfilled. Okay, x15 plus x25 plus x35 is equal to 4,000. We now need to put non-negative. Non-negatives, we need to write all the variables and say greater than or equal to, meaning we cannot supply negative number of kgs. There's nothing like negative 2 kgs of flour. You get the point, right? So they have to be positive. So we're just putting a non-negative function here, where the demand will be maybe denoted by I. So we shall say xi summation xi, or let me just say xi's, and then the supplies will be J's, and then Xij's should be greater than or equal to 0. I've done this to summarize because this requires that I list all the variables x11, x12, x13, x14, x1, all the 15 of them. There are 15, right? Yeah, all the 15 of them, and then suggest that they are greater than or equal to 0. So to summarize, I can simply say Xij, representing the supply, and then J representing the total of the demands should be greater than or equal to 0. So this is how you formulate the linear programming for a transportation problem. Thank you so very much.